Good morning. So in the last class we have seen the conditions for constructive and destructive interference in terms of path difference and phase differences. So the distribution of intensity or the variation of intensity can be shown in graph as figure. If you are drawing the angle along x-axis, that is the phase difference 0, pi, 3 pi, 4 pi, etc. And here negative, minus pi, minus 2 pi, minus 3 pi, minus 4 pi, etc. And we don't need this negative y-axis, and this x-axis is marked with the phase difference phi, and the y-axis as intensity. And so sorry, here we have taken the phi, the phase difference as delta, so this is delta. Whether it is phi or delta, it means the phase difference. So if you are substituting the value of 0, this value will be I is equal to 4I0, or the maximum value. So we can mark this point here as this 4I0 maximum value. And for the value delta is equal to pi, this is cos square pi by 2. That is cos square pi by 2 means I can show for delta is equal to 0, I is equal to 4I0, delta is equal to, for delta is equal to pi, I is equal to cos square delta by 2, because I is equal to 4I0 cos square delta by 2, cos square. Therefore delta is equal to pi means I is equal to 4I0 into cos square pi by 2. Cos pi by 2 is 0. Therefore intensity is 0. And similarly for delta is equal to 2 pi. For delta is equal to 2 pi, I is equal to 4I0 cos square pi. Okay, so cos pi is minus 1, cos square pi is cos pi is minus 1, so cos square pi is 1, which is nothing but 4I0 again. And this, so we will get 4 pi, it is 0, this is the point, and for 2 pi, this is the maximum value, 2 pi. And again we will get for 3 pi, it is 0, and 4 pi, it will get maximum value. And similarly in negative side also, for delta is equal to minus pi, I equal to 0, and for delta is equal to minus 2 pi, I is equal to 4I0, etc. You can check for another values if you have any doubt. And we can mark this point here, minus pi 0, 2 pi it is maximum, and 3 pi 0, 4 pi it is maximum, and the graph will be like this. Okay, so the intensity distribution of this interference fringes will be like this from this expression. This expression we have derived in the last class, and this is the graph showing the variation of this intensity. Okay, so we are discussing the theory of interference fringes today. In order to observe a stationary interference pattern, the sources of light producing interference must be coherent. So we need a coherent source. That means sources which send waves of same amplitude, same wavelength, and of same phase or constant phase difference. So a coherent sources can produce interference fringes. So in 1801 it was Thomas Young who demonstrated the phenomenon of interference light by double slit experiment. So this is the double slit experiment demonstration. So these are two slits, S1 and S2 are two slits, and these slits are illuminated with a source from here, somewhere here. A source is placed, a monochromatic source of light is placed, and this light is falling on these two slits, and a screen is placed here at about 1 meter distance from these slits. So these slits are very close to each other, and this picture is a very enlarged one, and the light from these slits are falling on this screen and produce alternate dark and fringe pattern on this screen. So we can see, or we can check how these bright and dark fringes are produced on this screen. So the monochromatic light waves spreading out through a slit were made to fall on two very fine slits, S1 and S2, which were parallel and very close to each other. So these rays are almost parallel, though this figure is drawn like this. This is an enlarged or exaggerated figure. So these rays are almost parallel because these slits are very close to each other. So there is no much difference in the path of this light waves. So the waves spreading out these slits superimpose on each other, and resulting interference was obtained on a screen. So when the light waves passing through these slits at some points it interferes and produces fringes, and when we are keeping a screen at this point, we will get fringe pattern on this screen. This was an experimental demonstration. So the interference pattern consists of equally spaced alternate bright and dark bands with a central bright band. Okay. Now the path difference between light waves from S1 and S2 reaching at the center is 0. That is, this is the center point. This is the center of these slits. This S1, this is S2, and the center of the slit is 0. Sorry, center of the slit is C. So if you are drawing a line to the screen, this point is marked as O. So the light reaching here and reaching here. So the path difference, this is the path traveled by this light wave to reach here, and this is the light wave travel from here to reach here. So S1O and S2O. This is O, not 0. S1O. This is S1O, and this is S2O. So S2O minus S1O will give the path difference between these light waves. It is 0 because this is the central point, and it will travel equal path from here and here to reach here. So the path difference is 0. Okay. Now let P be a point on the screen which is at a distance of y from the central point. So P is a point on the screen which is a distance of y from the central point. Then the path difference between light waves reaching at P from S2 and S1 is, so this is the path traveled by light from S2 to P, that is S2P, and S1P is the path traveled from the light from the slit S1. So S2P minus S1P will give you the path difference between these two light waves which travel to the point P. Okay, and so if we are drawing a perpendicular to this S2P from the slit S1, this difference, that is S2N. S2N is the difference between these two lines. That is, the path difference S2P minus S1P is nothing but S2N. So these two paths have difference which is equal to S2N. So this much difference only appear between the paths of S2P and S1P if you are drawing a perpendicular like this. From this distance, that is S1P and NP, this distance, these paths are equal. So this is the path difference. S2N is the path difference between S2P and S1P. So we have to find out S2N, which is the path difference between these two lines. Okay. Now, so we can now find out the path difference. So from this figure, this is the path difference S2N between the rays S2P and S1P. So from the triangle S2 S1N or S1N S2. This is the triangle I have marked here. This is angle theta and this is right angled triangle. Okay, and this angle, this is also theta. Okay, these slits are very close to each other, so this angle is very small, and also this angle will be very small like theta. So from this triangle S2N minus S2N by S1 S2. S1 S2 is the distance between the two slits S1 and S2, which is D. So we have marked here S2N by S1 S2 as 5 by D because S2N is the path difference which is 5 and S1 S2 is D, which is the distance between the slits. So we will get 5 by D. So left side is sine theta. So 5 is equal to D sine theta, which is equation 1. Now since the slits are very close to each other, D is very small. Therefore, in triangle OCP, angle PCO is theta. Triangle OCP. OCP means OCP. Angle PCO is theta because this angle and this angle will be very small, which I have explained just before. That is, these two slits are very close to each other, and so this angle is theta and is very small, and similarly this angle. So this angle and this angle is theta. Okay. So from this, so these two angles are theta. So from this triangle PCO triangle, tan theta is equal to OP by CO. OP by CO means OP, opposite side by adjacent side. OP by CO. Yes, CO. Okay. So we will get y by capital D, because this distance is y and this distance is between the source and screen, which is capital D. So CO is D is the distance between slits and the screen. For small value of D, angle theta is very small since S1P and S2P lie close to each other, which I have mentioned just before. Therefore, sin theta is approximately equal to tan theta, which is nothing but theta, since the angle is very small. So, from this figure, we can see that sin theta means from this triangle sin theta is equal to tan theta. Both are same, converge to the same value, and which is nothing but theta, since the angle is very small. Using equation 1 and 2, these two equations, what we will get? So we can equate these two equations, this equation 1 and this equation 2. So if we are equating these two, we will get d sin theta is equal to, or d theta, sin theta will now become theta. So d theta is equal to y d by capital D. Okay. So this is one equation. If nth bright band is formed at P, so at the point P, if you are getting a bright band, then the path difference phi can be written as n lambda, which is equal to y d by capital D. Okay, so we have seen the condition for bright band, which is equal to n lambda. So the path difference can be equated to n lambda is equal to y d by capital, which we have just seen before. From this, yn is equal to n lambda capital D by small d. So this is the condition for bright fringes that occurring at point P. Okay, now if n is equal to 1 in the above equation, we will get y1 is equal to lambda capital D by small d, which will give you the position of first bright band from the point O. From the point O means this point. So we are looking at this point. So the first bright band from O will obtain at a distance of y1 is equal to lambda d by small d. Okay, where lambda is the wavelength of the light, d is the distance between source and screen, and small d is the distance between the slits, separation between the slits. And if n is equal to 2, y2 will get 2 lambda capital D by d. And if n is equal to 3, y3 is equal to 3 lambda capital D by small d, which will give you successively second bright fringes, third bright fringes, etc. So the distance between these two fringes, any two fringes, this bright fringes, any successive bright fringes will give you the bandwidth of this. So we will get on the screen first bright fringes, the bands, and second and third, fourth, etc. This is at a distance. This is the point O. This is the point P. This is the first bright fringes, this is second, third, etc. And the distance between any two fringes will give you successive. Any two successive fringes will give you its bandwidth. So this is the bandwidth. So this can be between any two. So the separation between or distance between these two fringes will give you the bandwidth beta. So we can calculate the bandwidth from this expression like this: beta is equal to y2 minus y1, or general, this is between the separation between the second bright fringes and first bright fringe. And in general we can write yn minus 1, that is nth fringe and n minus 1th fringe. So if we are substituting the values from here, we will get we can substitute the values for y2 and y1 here. For in general, in terms of n, we can substitute like this: and it will converge to beta as lambda capital D by small d. So this is the bandwidth of the successive fringes which produced on the screen. And if you are finding the dark fringe and dark fringe at B, then the path difference 5 can be written in terms of written as 2n plus 1 lambda by 2. This is the condition for dark fringe which we have seen in the last class, and which is nothing but y small d by capital D, which we have derived before, just before. So if the fringe is dark, it should satisfy this condition. So we can equate this like this, and from this we will get yn is equal to 2n plus 1 lambda capital by 2d. So this is the condition for dark fringe which appear on the screen. Okay, and the condition for bright fringe was this. Okay, and the condition for dark fringe is this. Now we can find the bandwidth, that is in order to find the bandwidth we can find out two successive dark fringes by substituting the value n is equal to 0, 1, etc. For n is equal to 0, y0 is equal to lambda d by capital D from this expression. Similarly, for n is equal to 1, we will get y1 is equal to 3 lambda capital D by small d, so which will give you the second dark band from the point O. So the distance between any two successive dark band will give you the bandwidth. So on the screen you will get this is the point O, bright, that is this blue lines is bright fringes, and red is for dark. Okay, so we'll get alternate bright and dark fringes on the screen. You know why this alternate bright and dark fringes is obtaining here. We have seen the intensity distribution curve like this. Intensity distribution of the interference pattern is like this. This is bright point, this is dark point, this is bright point. See, this is bright, this is dark, bright, dark, etc. This is constructive interference, this is destructive interference, constructive, destructive interference, etc. So we'll get alternate bright and dark fringes on the screen after superposition or after interference. Okay. So any separation between these two, this successive bright fringes will give you bandwidth, or any separation between any two dark fringes will also give you beta. So the beta can be found out from any bright fringes or dark fringes. Okay, so from dark fringes we can find out the beta, the bandwidth as y1 minus y0, or from general expression yn minus 1, which from these expressions we will get, substituting here, we will get lambda d by small d. So we have got here the bandwidth as lambda capital D by small d from dark fringes, and from the bright fringes we have also got lambda capital D by small d. So these two equations shows that both bright and dark fringes are of equal width. Okay, so we get we will get on the screen alternate bright and dark fringes of equal width on the screen. That is the interference pattern we are obtaining on the screen from this Young's double slit experiment. So how this bright and dark fringes are produced. We have seen the superposition principle in the last classes, and also the theory, also the interference intensity distribution. So light from the point, I can show. So light from the sources is passing through the slits, and it superimpose each other, and on the screen according to the condition of the constructive or destructive interference, whether the path difference between these two light is satisfying the condition for constructive or destructive interference, we will get maxima and minima points, or bright and dark fringes on the screen. That's why we are getting bright and dark fringes on the screen. Okay, so this is the theory of interference. Now since beta, the bandwidth is proportional to lambda, we can see from this expression beta, the bandwidth is proportional to the wavelength. Larger the wavelength, larger is the bandwidth, and vice versa. If the wavelength used for producing this interference pattern is large, then the bandwidth will be large. Okay. So in the conditions for sustained interference pattern are, in order to produce a steady interference pattern, some conditions need to be satisfied. So the conditions for sustained interference patterns are conditions for sustained interference pattern. 1. The sources must be coherent. Coherent sources must be that is two sources producing same amplitude, same frequency, and constant phase difference waves. And the two sources must be monochromatic, a single wavelength source, monochromatic sources, and the separation between the two coherent sources should be small, so that the width of the bright and dark bands will increase, and hence good visibility of the fringes. That is D, the separation between the slits. We have made the separation, that is separation between the sources, should be small, and also two sources should be narrow sources should be, I'll explain, and the distance of the screen from the coherent should be of quite large. Source screen distance should be large. Sorry, this is not the figure. I will show you from this figure. So this slit S1 and S2 is used for the purpose of producing two coherent sources from a single source. If we are putting a source here and passing the light through two slits, it will access two different sources, S1 and S2. That's why we are using these slits here. So the purpose of slits S1 and S2 is to produce two different sources of monochromatic source. So if we are using a single wavelength source here, and we are spreading the light using two slits, so these two slits will act as two different sources. That's the purpose of using this slit here, and the distance between these two sources should be very small. Okay, so that's all about the theory of interference fringes. Okay, thank you.